Okay, so this is the explanation for the lecture notes that will uh, try and help explain for you the predator-prey interactions diagrams that we have up on the web for class. And so the first thing we want to think about are the equations that are here in the upper left component of this slide. The idea is that we can take our exponential growth equation, dv dt equals rv, where we've changed n to the letter v for victims, and that is an exponential growth equation. And then we're going to add in this component, av, which is a function of how predation affects the predators, and then p, for the number of density of predators. And so what we want to find out is a place where dv dt equals 0. And so we can do that by rearranging the oopsie, that didn't work. Rearranging the equations to set rv equals to avp. That's just moving avp around the other side of the equation. V cancels out on both sides of the equation, and so that the density of predators that where the victim's population size doesn't change is R divided by A. And that then is reflected in this red line right here. That's a threshold density of predators around which prey populations won't change, and above that suggests that populations of that red line victim populations will decline. That's the red dashed arrow moving towards your left. And below that the p-hat line, victim populations would tend to increase, and that's the dashed line moving to the right. And that means would change through time. Going back up to these equations again, we see that similarly we'd like to change the exponential growth rate equation now to say that the change in the density of population of predators through time has something to do with the birth rate, and that birth rate is modified by how the eating victims affects the fitness of the population, minus some death rate for the predators. Similarly, if we set that equal to 0, what we can do is move things around from one side of the equation to the other, and that is the same equation. Predators cancel out on both sides of the equation, and then in order to figure out what the density of victims would be, we simply divide both sides by that BA, and there you have the threshold density of victims above which predator populations increase, as indicated by the upward pointing green lines, dashed lines on the lower graph, and below which the predator populations would decline for lack of prey, indicated by the downward pointing green dashed lines. This results in some several dynamics that we can display here by looking at changes in population size through time. And so these dashed lines indicate change from one time step to another, and that we can continue to think about these things by saying if predator populations increase through time and prey populations decrease through time, that the net change in the population would be to increase predators and decrease prey. So that means that direction. And that from this you can see that the trajectory of the population might cycle around in a counterclockwise fashion. My pen is jumping around me like this, but you get the idea. And around and around and around as predator populations increase and decrease and increase and decrease through time. So that in the upper right-hand corner quadrant of this graph, we have high populations of both predators and prey. In the lower left, we have low densities of predators and prey. On the upper left, we have high densities of predators, low densities of prey, resulting in the declining populations of both sets of organisms. And down the lower right, we have low densities of predators but high densities of prey, again resulting in the increase in both sets of those kinds of populations. So now we can link this to what a predator-prey cycle might do in time, and I've set this up in advance already. But here we have in the light blue line a cycle of prey which increases, which then allows for more prey resources for predators. Predator populations increase. As predator populations increase, they cross some threshold and begin to drive those prey populations down. And that as the prey populations go down, then predator populations start to go down, and we see this cycle go around and around and around. Okay, so what I said in class was that there are two kinds of questions that I could ask of you. I could say, given a quadrat, find the place on the diagram where that exists. Or I could say, given a point on the predator-prey cycle diagram, which quadrat would that be in? So let's just take a look at these and try and do that problem. I'll do it in this direction, but not the other direction, and you can figure it out the other direction. So right here we have a case where predator populations, as indicated by the heavy blue line at the letter A, are increasing, and so are the populations of prey. Well, where would we find the conditions under which predator populations and prey populations were both increasing? Well, in order for predator populations to increase, the prey populations have to be relatively high, so it has to be over on this right-hand side of the graph. And in order for prey populations to increase, the predator populations have to remain relatively low, so it has to be down in this corner of the graph. And in fact, when we look down in this corner, we see that prey populations and predator populations, the green arrows and red arrows, are both increasing. Moving on to the other one that's like that, D here, this is where both prey populations and predator populations are declining. And where would we find predator and prey populations both declining? Well, when predator populations are relatively high compared to prey populations. And so the predators are still preying upon lots of predators. The predator population is still exerting a force that causes decline in the prey populations, and there aren't sufficient prey to support that predator population. And so if we look over here, that is where we find here in this corner, upper left, where we find that predator populations are relatively high, prey populations are relatively low, driving a decrease in prey populations with the red arrow going to the left and the green arrow, and also predator populations with the green arrow going down. Okay, that leaves us to two where the populations are going in opposite directions. And so let's just start with B and look at that one and say, well, where would we find conditions under which prey populations are going down, but predator populations are still going up? Well, that's where prey populations would be very high, but predator populations would be also relatively high. And so, and both those populations are relatively high. So where do we find this, that predator populations are going up and prey populations are going down? That's up in this upper right-hand corner here. And that leaves us the fourth case, which we would have by default, but let's go talk it through anyway. And that is, where would you find the case where prey populations are beginning to increase, but predator populations are beginning to decrease? Well, when predator populations are very low and prey populations are very low, then you have the conditions under which predators are not exerting enough control over prey to decrease the population, and there aren't enough prey around to fuel population growth in prey, and that's right down in here. And so you can see these fit both with respect to the number of predators and prey and also the slopes of the lines, and that's how you would sort out that problem. And so now you could also see how you could do that problem in the opposite direction, where if I gave you the letters of the quadrats and asked you to place points on a line corresponding to each of those places that you could simply take these lines and put them in the appropriate place of the graph. All right, good luck, and talk to you soon.